All right, y'all, so let's look at the limit definition of a derivative. So the first thing I want to do is look at a particular curve, talk about the tangent line at a particular point on that curve, and use that to develop something called a derivative. That way we can give meaning to what a derivative is telling us, and we can also find the derivative using a limit. So let's go. Okay, so this question says find the equation of the tangent line to f of x is equal to x squared at the point 2, 4. So if you remember, the two things you need to find the equation of a line is a point and a slope. So obviously we have the point. We want to find the equation of the line that goes through the point 2, 4, but we need a slope. So how do we find the slope of this particular tangent line, which I have in purple? Okay, so how I like to talk about this is to first just review the slope formula. So we all know slope is the change in y over change in x. But I want to look at the slope formula using function notation. So if you remember, the y value is the output value, which represents the function value of a particular function. So instead of writing this as y2 minus y1, I want to write it as the function of x2 minus the function of x1 all over x2 minus x1, like this. All right. And so now what we want to do is, at this point, you've probably learned how to approximate the slopes of tangent lines using secant lines. So you could imagine finding the slope of the secant line, let's say through the point 2, 4 and 1, 1. And so what you could do is find the slope of that secant line, and then to approximate or to find the slope of the tangent line at the point 2, 4, that we want that point to be our point of tangency. What we would do is take the point 1, 1, which was used to find the slope of the secant line, and move it, trace it along the curve, and move it closer and closer and closer to our point of tangency, our intended point of tangency. So in orange, I would first find the slope of the secant line. So just find the slope between the points 2, 4 and 1, 1. Okay, and we could use that to then take the point 1, 1 and pull it closer. Maybe go to the point 1.5 and the function value there, or 1.9 and the function value there, or 1.99. And the idea is to pull it closer and closer and closer to that point of tangency. Find the slope between 2, 4 and the points as you get closer and closer to that point of tangency. So as I pull it closer, find the slope between that point and the point of tangency 2, 4, and then pull it even closer. And the idea is we want to get it as close as possible to that point 2, 4, and then find the slope between 2, 4 and those points as they get closer to the point 2, 4. And what you're doing there is using something known as a limit to find the slope of what will eventually become the tangent line as you pull them points closer and closer and closer to the point of tangency 2, 4. So you're doing a limit there as you're finding that slope between those 2 points. Okay, so let's look at what we're doing with that idea in a limit notation. So the slope is going to be the limit as, let's call the point of tangency x1 and then the function value at x1. All right. And so that means the x2, the function value at x2 are going to be the points as we get closer and closer and closer to that point of tangency. So in other words, my x2 value is going to be getting closer and closer and closer to my x1 value. So my limit is going to be the limit as x2 approaches x1 of the slope formula. Okay, so there's the limit. The slope is going to be the limit as I pull that point x2 closer to x1 of the slope formula, the rate of change formula. Okay. And so don't let the subscripts get you too mixed up. They're just subscripts that represent different x values. So now let me pull back up. The function, let's take note of the function. If I plug in those values as I get closer and closer to my point of tangency, I don't know what they are. I do know what they are. They're 1.9, 1.99, 1.999, but they keep changing. So I'm going to keep it in general. Those points continue to change, and so I'm just going to say I'm plugging in the value x2. So when I plug in my value x2 into my function, I'd simply just get x2 squared because my function is x squared. So the limit as x2 approaches, we'll leave that blank for now, but the function value here at x2 is simply going to be x2 squared. Now the function value at x1, well, our x1 is the x value at our point of tangency, so we have already determined that that is the value 2. So what is the function value when your x value is 2? Well, that's just the y value, right? Which is 4. So we already have our function value at x1 and x1. So we just kind of plug those in. So minus the function value at x1, which is 4, over x2 minus x1, which again is 2. And so from here, we just calculate this limit. We cannot use direct substitution yet because that gives us an undefined value. So what we want to do is try to factor and see if we can reduce the x2 squared minus 4 over x2 minus 2. And hopefully you remember this is a difference of squares, and so this would become the limit as x2 approaches 2. The difference of squares there will be x2 minus 2 times x2 plus 2 all over x2 minus 2. And we want to factor there because now we can see the x2 minus 2 factors do reduce, and we are left with the slope is equal to the limit as x2 approaches 2 of x2 plus 2, which was what was left here. Now we can use direct substitution because we don't have any issues in terms of being undefined. So if we just plug in our value 2 into the x2, so in other words, take this and plug it in there using direct substitution, we'll find that 2 plus 2 is equal to 4. So that is the slope of my tangent line. All right, so let's pull this up a little bit. So now that I know the slope of my tangent line, that purple line, I know the slope there is 4. Okay, and the point of tangency is 2, 4. So now I can find the equation of that line by first putting it in point slope form. That's what I like to do first. Point slope form looks like this. And so now I know my point, I know my slope. My point is the point 2, 4. My slope is 4. Plug all that in. So I get y minus 4 equals, the slope was 4, x minus 2. Okay, and if we were asked to represent this equation of the tangent line in slope-intercept form, which is commonly used, if we distribute that 4, we'll have y minus 4 is equal to 4x minus 8, and then isolate y by adding 4 to both sides, and you'll have y is equal to 4x minus 4. There's the equation of the tangent line at the point 2, 4. Now, what we did there, we had to find the slope of that tangent line using a limit, and I hope that explanation helped. And so that leads us into what a derivative is. The derivative is a function's output relative to a function's input at a particular point on that function. So you may hear the words instantaneous rate of change or instantaneous velocity. So if I look at my curve here, at this point of tangency, my instantaneous rate of change, so the change in y over the change in x, is the slope of my tangent line. And so the derivative is simply the limit as I pull x2 closer to x1 of the function value at x2 minus the function value at x1 over the x2 minus x1 values. That is one of the two notations that I want to introduce to give you the limit definition of a derivative. Now, the one thing I haven't done yet is give you the notation of a derivative, which will come. But I want to go ahead and introduce another notation for the derivative, and that is using the difference quotient. And so we could say the limit as h approaches 0 of the function value x at x plus h minus the function value at x over h. And remember, we've discussed in previous videos the difference quotient. What I want to do now is include the notation for a derivative. And so the derivative would be the notation. There's a few different notations. I just want to introduce the one notation here, which is f prime. So if I have a function f of x, this is going to give me f prime at x1. I'm specifically saying x1 because I have that labeled here, right? And we can make the relationship between that previous example and this notation. But using the notation below, using the difference quotient, I can just say that this is how you find f prime x. So what I want to finish this video with is finding the derivative as a function using what the notation that I've just put in a red box. So let's do that real quick. So here's the question. The question is, find the derivative of f of x equals x squared using the limit definition of a derivative. So the limit definition looks like this. Now remember, what we want to do is take x plus h, plug it into our function. So this notation means take the expression x plus h, plug it in there. We'll have f prime is equal to the limit as h approaches 0 of x plus h squared. And then we say minus f of x, which is the function, right? Minus the function, which is x squared, all over h. Again, FOIL the x plus h squared. All right, reduce when you can. And then you'll be left with 2xh plus h squared over h. Remember, we want to get to a point where we can plug 0 in for h. So you could factor an h out of the top, which reduces the h in the denominator, or you can just simply say all three of these terms share an h, and so we'll be left with, once we reduce, we'd be left with, and so now we can use direct substitution, plug in 0 for h, and we'll get the derivative f prime of x is equal to 2x. And so that is the derivative as a function. So now if my function is x squared, then my derivative is 2x. And so if I wanted to find the slope of a tangent line at any point on the curve x squared, I would simply take that x value, plug it into my derivative, and that gives me the slope. So in other words, the example we did earlier, we found the equation of the tangent line at the point 2, 4. And so our point of tangency was at the point 2, 4. The x value there was 2. If I plug 2 into my derivative, I get 2 times 2, which is 4. That gives me the slope of my tangent line. So now I can use the derivative and find the slope of the tangent line at any point on the curve x squared. So what is the slope of the tangent line at x equals 1? Well, take 1, plug it into the derivative. You'll find that that slope of that tangent line would be 2 times 1, which is 2. What's the slope of the tangent line when x is negative 3? Well, that would be negative 6, and so on. And so that is the use of the derivative, and we just found it using the limit definition. Again, at this point, you've used the difference quotient, and so now just stick that limit as h approaches 0 in front of that difference quotient formula, and that is the limit definition of a derivative. Alright, so I hope this helped out. Let me know in the comments. See you in the next one.